So now we're going to start in on digital logic, the types of circuits that make computers work. The first and most basic logic gate is the inverter. The symbol is an arrow with a bubble on it. The bubble means that the output is inverted. Without it, it would just be a buffer. With the bubble, it inverts the output. So, the state table is, you have your A, your input, and your output, and you do all combinations of possible inputs for the device, 0 and 1. So the output, being an inverter, is going to give you a 1 and a 0. If the input is a 0, the output is a 1. If the input is a 1, the output is a 0. Like I said, it's the most basic gate. It's also the most simple electronically. It is most simply come on. Implemented using one transistor and one resistor So if the input is 0, this transistor is turned off and power goes out. If this input is a 1, the transistor is turned on, the switch is turned on, the switching transistor, and it creates a short to ground, and the output is pulled to ground. Because there'd be no resistance between out and ground, where there would be a resistance from out to power. So it takes the charge from the easier path. So this is how basically a inverter works. In actual practice, I believe they use 2 transistors, but either way, it's the simplest implementation would be to do it this way. And, the second type of logic gate would be the AND gate. Its symbol is that. And the state table, I'll do the state table here, A, B, out. Now with 2 inputs, you can have 4 combinations of possible inputs. So you have to give all of them in the state table. 0, 0, 0, 1, 1, 0, and 1, 1. Now the AND gate is, as the name implies, it's high. It gives you a 1 if both A and B are 1. So it would give a 0 for here because A and B are not 1, both 1, and then a 1 for the B, or for the A and B equaling 1. Now this is a little bit more complex for the schematic diagram for it. All right. It's 3 transistors minimum. Again, in practice, they use more to have cleaner outputs, but basically, if A and B are, if one of them is 0, one of the 2 transistors is going to be turned off, sending a high signal here, and this acts as an inverter. So if the high output here will generate a low output here, if either A or B are both, or either one are 0, and one or both of the transistors is turned off. If both transistors are turned on, then this creates a short and brings this low, turns this transistor off, sending a high signal out. But the key to this is the 2 transistors here are in series, one after another. Now you can have multiple input AND gates by just adding more transistors in series. Add a 3rd transistor down here and have a C input, and then all of the inputs would have to be 1 in order for the output to be 1. And that would be a 3 input AND gate. Now, what is interesting is the existence of a more simple form of this gate, the NAND gate, which is the same symbol but has a bubble here indicating that the output is inverted. And the schematic diagram is the same as the AND gate, except no inverter. So it uses fewer transistors. And the truth table for it is 1, 1, 1, 0. The exact opposite of the AND gate. Yeah. No, they are not. Good question. A truth table has two values, true or false. A state table can have more than one state, or more than two states, depending on the device that you're dealing with. For what we're dealing with, they're basically interchangeable, but the proper term is a state table for logic devices, because there's the high impedance state, there's the undetermined state, and a few others that can be the result of an operation. You get more into those in digital logic class later on later in the semester in digital logic class. But some textbooks use the term truth table for these for tables for logic devices. Technically, that's wrong, but it's passable as, for basic purposes. I prefer to use the proper term state table. But the bubble on the NAND gate indicates that it is inverted. Otherwise, it looks like an AND gate. When you see a bubble, that means the input or output is inverted before it goes into the it goes into the gate, or after it leaves the gate. So just keep in mind that those bubbles, they mean different things. They mean a different output than from a regular AND gate. Let's see here. Then we can move on to the third basic gate, the OR gate. The OR gate has a different shape, and the state table now you might have guessed from the name that it is high when either A or B is high, or 1. So it's 0, 1, 1, 1. Now, where the multiple transistors in an AND gate were in series, the transistors for an OR gate are in parallel. See the two transistors are in parallel, either one being low or being high. I'm sorry. Either one being high will short the output, what would be the output to ground, and turning off this transistor, which would have the power go to out, making it high. Again, you might recognize the inverter. It is a inverted output internally from what would be a NOR gate. So, and you could add inputs by adding more transistors in parallel before the inverter inverts the output. So if you take away the inverter, you have a NOR gate, which has the inverted outputs, and then you would just take away the internal inverter, and just left with the two transistors for the logic. So those are the 5 basic gates that you're going to run into mostly in digital logic. There's one more gate that I don't know how it's implemented with transistors, but it's going to be built with and NAND gates, or with the basic and, or, and not. The exclusive OR, which is used in mathematical operations. We'll get to that one next time. In the meantime, I think that it is enough to swallow for one day. Any questions about the logic gates that I covered today? I know I covered it pretty quick, but they're pretty basic items. The state tables should eventually be memorized. Save that for digital logic class. No questions? Okay, I guess we'll call it a day then. Have a good day. See you on Monday. Yeah.